Good morning, colleagues. So we are happy to back to this very nice lecture for today. And yesterday we had Professor Lee from Zhejiang U. Today we have Professor He from Zhejiang U. Professor He, he is currently now in physics. He actually is working for one time director for the Center of Brain Imaging Science and Technology. Let me introduce him more carefully. So he obtained a bachelor degree in 2005 and a PhD in 2011, also from Zhejiang University. So they are classmates. Also, with Jingyan, your classmate. Yeah. yeah. Then he did postdoc research, and then he joined this College of Biomedical Engineering and Instrument Science in Zhejiang U. So he established this Center for Brain Imaging Science and Technology. So that's we found very relevant to us because we just established our life science imaging center with the MRI and TMS. So Christopher is an expert on this. So he moved back to physics department as professor there, and his research is mainly focusing on the quantitative mapping of complex brain network structure. So today he will talk about advanced method to use this machine to get better data from MRI imaging. So thank you.
Thank you for the invitation and introduction, and thanks for inviting me here. It's my great honor. Just as Professor Zhou introduced, I was working. I am still working in the Center of MRI Imaging. I moved to School of Physics because I want to touch more deeper scale about the brain and trying to do some multi-scale integration. And that's the topic I want to collaborate with Chan Song's group. So when Chan Song first discussed with me about this talk, I think this topic would be very related to the group here, because you just installed the new Prisma scanner, which I have run for like around about 10 years. So let me just start the slides. So I think MRI could be most of the audience would be fresh to MRI. So I think it's my obligation to just give a very brief introduction to MRI basics. So it will be very straightforward as I expected, but I hope you will enjoy it. So my talk will be includes 3 parts, and the first part is the MRI basics. So in MRI is the most prominent neuroimaging technique for human brain imaging, and it's used for a lot of different human brain projects in different countries. Like right now, the Chinese brain project using we just joined the triad project of Chinese children. So it includes more than 30 sites, which like 90% of them are using the Prisma scanner. So we use MRI because it has very exact soft tissue contrast in different imaging, and it gives you different various of imaging modes, like T1 image, T2 image, and also functional diffusion imaging, like as I showed here. And MRI is one property is very safe. It's non-invasive. You don't need to inject any dose into your body, and it has no anything radiation problem. So the other thing is very economic. Is quite cheap compared to the other modality like PET studies. So talking to MRI basics. So I think maybe a lot of audience are here from physics department, if I'm right. I think people should be familiar with proton spins. In our body, we have a lot of water. So each water have 2 protons, and the protons will rotating, which is precession in the electromagnetic. And we can have this precession equation here. to describe its movement. The important thing is this rotation will have a particular frequency, which is a Lama frequency. And you can write down the equation like this frequency equals to gamma multiplied by B0. So when we have our 3T, for example, you have this 3T, then the frequency is just fixed to 180 amp-hertz. And if you are able to change the magnet field, so for example, it's 1.5T to 7T, this frequency will just change linearly. That's why I just made this an analogy to a radio. I thought I was first to think in this way, but one day I opened a Siemens magazine and they are using this analogy as well. Because when you are using this radio, you just tune to a specific frequency, you'll get the information, right? So our MR scanner will only pick up the particular information from this B1 field, which is running at the Lama frequency. And this B1 field will tilt our magnetization to a to some angle which you can control. It's very nice. You can control from the amplitude of this radio frequency field and also the time duration. Then you will get the desired angle you want, for example, the 90 degree, 180 degree, like that. This, just as I mentioned, this flip angle is determined by the direction of this B1 field and the amplitude and the duration. Then after that's the step of the excitation. After this excitation, the spin will just experience a dephasing procedure. That means different spin will have different frequency a little bit because the local field homogeneity. Then when you apply another 180 degree, if you do nothing, this the entire transversal magnetization will just decay to zero. Then, but when we can apply another 180 degree pulse, then you can reverse everything to it's the other way. Then all the spins will go together, which is the final procedure. This entire procedure is actually called a spin echo. You could see the dephase and the rephase progress. That means you add this 180 degree pulse is called the refocusing pulse. And most importantly, our echo time is actually equals to the 2 tau. This is the total time from this one, from here to here. So we just defined the echo time. Echo time is most important and the fundamental parameter in MRI. You can see this is a diagram of very simple spin echo sequence. We have this TE time, which is the echo time I just mentioned, and also the repetition time with the TR. You actually just adjust the combination of TR and the TE to get a different contrast. So comparing to this one, we just make the T time much longer to adjust the T2 weighting. So this is a signal equation of the spin echo signal. You can see here the signal, if the final signal you got is actually equals to the polar density is proportional to S0 and as now, and this is a T1 weighting. You can see when you increase the TR time, actually this will eventually go to 1, right? And but if you increase the T time as I'm doing here, this part will getting smaller and smaller. Then the reason for this guy getting smaller because the different spins will just spread out. So this is a comparison from T0 to T short T and the long TE. That's why I'm saying you making the TR, you adjust the TR time, you are adjusting the T1 weighting. you change the TE time to adjust the T2 weighting. So the decay ratio, if I got two tissues, different tissue will have a different decay ratio, like I show here, the blue and the red one. The important thing in MRI is you're trying to maximize the tissue contrast, which the signal difference between this blue and the red tissue. So, for example, in this case, if you choose TE here, you will get the maximum contrast between these two tissues. So that's why I'm saying the choice of TE determines really the TR contrast of our image. I give you a simple example. You fix the TR time here, but you already change the TE time. You get it like a TE equals to 25 milliseconds to 100 seconds. You can see the image, how the image varies. Okay, so this is how the T2 weighting changes according to our TE time. So this is a very basic, and we can just start from here. As I just say, in a very simple case, you have two different tissue, and these two tissue will have different T1 value. That means they recover to their equilibrium state in different ratio. So this blue one will go faster, and this yellow one will go faster, and the blue one goes slower. But if you set your TR time to like 3000, for most of the tissue, we say the T1 recovery also have already reached around 90%, which is also almost equals this guy equals almost to 1. Then the entire signal will be determined by TE only. So you have short TE, then this contrast will be somewhere here. But if you choose your TE here, then the contrast will be determined by this gap. So in the topic of diffusion imaging and functional imaging, I'm going to introduce later. The TR time is always selected to be long enough, like 2,000 or 3,000, or even 5,000 milliseconds. So that means we can ignore the contribution from T1 effect in my later materials. Then the left thing is T2 is the main source of the contrast, which we are going to deal with. The interesting is, in my previous part, we always assume if this is one voxel, even though the composition is quite complex, but we always assuming the voxel will have one T2. That means the entire tissue is quite homogeneous. So you only have one T2. But in reality, we know if the signal, if this voxel you have like I'm showing here is a white matter voxel. You have this axon and wrapped by the blue things is the myelin, and then you have this green things is the actual cellular part. So basically, you can very easy to see if we ignore this blue one, the myelin signal, you still got the intracellular and the actual cellular water. Different water give you different T2. So basically, it's very straightforward for us to think maybe we will not only have one tissue type, we have two or more tissue type within an imaging voxel. Then the T2 value, we cannot assuming they just simply equals to each other, right? So we'll have T2 value be valued between different tissues. Then the entire signal will be not only the first part, we will have the contribution from both tissues, which as I write down here. So this B should be the subsurface. So you have different contribution. If you set your T value, you have different contribution from different T2 tissues. So this is a basic part. I go very quickly and hope you get the whole idea. The most important thing is for the next story is following this equation. Then I will go to the second part, which is a diffusion MRI. I will show you how our working hypothesis like this equation will impact the signal. In diffusion MRI, the main part is quite simple, quite similar to the spin echo I just introduced. The different thing is, and the most important thing is, in diffusion MRI, you have another gradient, which is called the diffusion gradient. you have this diffusion gradient, which is a very narrow gradient. It means this small delta will be, little delta will be quite small, and you have this big delta, which describe the water molecule move from one place to the other place. Because we add these gradients, and the gradient, this gradient, the red guy, if you add to in one direction, then the space will experience the motion from one place to the other place. The further it goes, then the signal decay due to this diffusion gradient will be much deeper, from this white this black one to this. Let me use this one. From this black, this is the original signal, and after the water movement, you will get the red signal. So you can see the signal decreasing due to the water molecular movement. And interestingly, we can just set up experiment. You can do B equal to 0. The B value actually proportional to the area of our diffusion gradient. You can see this is equals to this is gamma free this is gyro ratio magnetic ratio gamma, and this is small delta, and this is the big G. This is the area of this diffusion gradient. Then you can change your B value from 0 to different B value. You can then fit up the signal with using the log signal. Then you can get a very linear fitting. And this linear fitting, from this linear fitting, you can tell in different place how much this D value will be, which describes the water the movement of water molecule. But this will give you one D value for one voxel, and nowadays we're assuming the molecule won't go one direction, will go different directions. So we're using this tensor matrix. That means our list diffusion gradient will point to different directions. For example, we have 1, 2, 3, 4, 5, 20 directions. 15 directions here, and we'll give you different direction of our diffusion gradient. And you always can correct. You close this gradient, you can get this as non-zero, as images. And after you turn on this gradient, you will get different direction of the different image. So you try to fit the equation signal here, which is a tensor model. And we call this imaging metric method called the diffusion tensor imaging. You do a tensor diagonalization. You get in each voxel, you will get a sphere or like epilepsy here. So you get this main direction and the other two directions. You will know your water molecule actually moves in this direction much more than the other two directions. This is how the diffusion tensor imaging works. Then you can, from this tensor, you can get the estimation of scalar measures, which give you how faster this molecule moves. We'll call this mean diffusivity as MD values. And we can also calculate the FA value. We'll give you the fractional anisotropy, which is determined by this equation. So this is the two most important parameters in DTI images. Then our story comes back to T value. So as I show here, if you have this 90 and 180 degree pulse, and we will have another, we will form an echo after another. If we say this is a tau time tau, we'll get another echo after another tau. Then the T time is just determined by this duration, and you can see the diffusion gradient here. The thing is, if you run a study like a DTI, you go to a hospital, you are using some auto scanner, then this T value could be very different from what you can get or achieved on our Prisma scanner. For example, in my center, we use T value like mostly for 68, but we can last night just a hospital in in China, Xianya Yuan in Changsha, they sent me some data. Their T value is around 180 milliseconds. So it's quite like a previous version of Siemens scanner. So this is quite a key parameter in diffusion MRI. So when the T become longer, mostly because you want to increase the area of these diffusion gradients. So if the diffusion gradient hardware is not good enough, then after you increase the make this area bigger, then the T time has to be longer. Then that's why I'm saying T becomes longer for high B value images. But the good thing is as you have Prisma here, so you can easily, because Prisma have this gradient system, and as I'm showing here, a good diffusion system means you can achieve the same area but in a shorter time. Then that means you can, if you have the same B value with Prisma, you can have a shorter TE. Then the reason is in Prisma you have this G max equals to 80, and the slew rate it means the ratio of this slope is equals to 200. But you can compare with the conventional scanner, which is around 50 and 100. There's quite a difference. And with this good high performance gradient system, that will allow you to make your image TE be much shorter, or it can give you higher B value. For example, if you're using Prisma, you can go make the B value not only below 3,000, you can go even higher to 10,000, which I tested a lot in our center. And you can also choose to make your resolution from 2 millimeter thick isotropic voxel to 1.5 or 1.7 millimeter isotropic voxels. So as I'm saying, with Prisma you can do minimal T to around 70 and the maximum B value around 10,000. Then but also for the whole brain, but you need to using the technique called simultaneous multi-slice imaging. Another good thing is we choose the Prisma scanner, which is very good for, because of this merit. So it's very good for advanced multi-shell hardy imaging. That means you have many different directions, more than 60 or even 90 directions, and different B value for multi-shells. Another thing is, as I just mentioned, the T value could be very different for different scanner. But you can just simplify your study, just running your subject in Prisma, but you change the T value. Then you want to scan, instead of scan one time point here, that means like 7 minutes. So you will scan your subject for one hour. Only you fix every other parameters, and you only change the TE value. The interesting is, even though we are using the same scanner, you are using the same DTI model, and you are calculating the same FA value. But this metric, this scalar measure will be linear arising according to the TE value. That means you increase the TE value, this FA will, you will see the increasing in FA. But the thing is, you didn't see too much in MD value, but you also see this axial diffusivity, means along the water molecular will travel parallel to the axon, and this is the perpendicular to the axon, the RD value. You can always see this linear correlation. The thing is, people don't understand why, and this is repeated both in monkey brain and the human brain. So we're trying to understand why the phenomenon, this linear correlation will look in this way. We run a Monte Carlo simulation, which is quite familiar to our physics department. So you can build up your tissue organization like this. We are interested in the white matter, because the linear shape, you want to see this the previous linear shape in gray matter, you mostly see in the white matter. So in the matter matter, a simplified model is you have the axon, just I showed it before. This blue guy is the axon, and the orange guy is the myelin, and you also have the extra space. But I'm saying it's very simplified because you made all the diameter the same, and it's arranged in a parallel way. So the important thing is in this model, we're assuming the extra axonal space, the T2 value is quite shorter than the intra part. One is 60, the other is 100. Then we will, because of these two compartment model, then your signal model will be changed to this one, just as I mentioned previously. You will get this extra space signal and the intraspace signal. And I just write out this. The different thing is I made this T2 contribution out. Instead of previously we call this F equals both of them to be S now. Then if you have this model, you run the simulation, you will calculate the FA value. You can see very nice linear relationship of FA to this T value. It's very consistent with our in vivo study, right? Then, but if you decide your tissue composition only have one T2 value, then this linear shape will just go away. That tells us this T dependence have the microstructure basis. It's contributed by the compartment T2 of different tissues. And actually, in our this simulation, we also discussed about the potential water exchange, as the reviewer suggested. But I just say this water exchange is quite a controversial in diffusion. At the end, I decided not to talk more. The other model, which is more advanced, is assuming our tissue is composed by 3 different tissue types. Like you can have this stick, like the axons. You will have this very restricted diffusion where the water molecule will only go in this way or the other way, just parallel to the axon. And then you have this hindered diffusion, which is extra nucleate space, and you will also have the isotropic diffusion, which like more like the CSF signal. And this model is very popular now. It's developed by Gary Zhang in UCL group. So we just in this study is quite straightforward. If you understand the previous DTI study, we just recruit subject again and run. You can see run the study from different TEs. That means you will stay in the scanner for another 1 hour, right? The interesting is you fit this. This is the main parameter of the measurements Nordi model will try to give you. Then you have this intranumerator fraction, this ODI value, and the isotropic water fraction. You can see how this intrafraction will go up when you increase the T time. This is just a very similar thing to previous DTI study. But this ODI, which will give you the dispersion of the axons, then it doesn't change too much according to the T time. So it will tell you the intrafraction and the isotropic fraction increase with the T in white matter, but you cannot see too much in the green matter, as you see here, the outside of the brain. Stressing there's a difference in the T2 value, and no matter the T value you used, the intra and isotropic water fraction is actually overestimated. So we propose the idea to correct this effect. And the most important, if you do, because you have different T value, you can do a 2-compartment T2 fitting, and you will get this. This is the intracellular part, innulet part. This is the extranuclear part, the T2 value. You can see this T2 value. The extra part is around 50 or 60 somewhere, and this is around 100, 80 something. So it's quite similar to our previous study. And the message, take-home message is the same with DTI studies. Compartment-specific T2 would result in this T2 weighting contribution, as I show you here. Then again, we done another simulation experiment to prove this. And you can, because in the simulation you can set up a voxel signal which is purely white matter voxel, because that means it has nothing, has no free water inside, and you have increasing the fraction of free water. With this, I believe this is 10%. This is 50% or more than that. Then you will see the trend just increasing as I show in the in vivo experiment. The most important thing is this ODI value doesn't change according to the T value. And we in this paper we also introduce a way to correct the this T dependence, as I just mentioned, is as already estimated. Then, but you need at least 2 T's. That means if you for 1 T it will take you 7 minutes. 2 T will take you 15 minutes. It's not economical, but it's you can do it with some practical. So for now, it will. I think everyone will believe in with me. The T value will affect or will have great impact on your diffusion study. Then a further thing we did is by this Dr. Tong Qi. She collected with several tracking subjects. That means one subject will go to different scanner. I mean the clinical scanner and our Prisma scanner, because in the clinical scanner with the same settings, you cannot make the T value to as shorter as 7 milliseconds. Then this is going to be multiple T dataset with different T values. Then the thing is, you can with this dataset you can compare the interstandard variation. This is something you don't want. It's some error or only related to the scanner. Then the thing is, the intersubject variation is something you want to observe. You want to measure, which is an individual difference. The problem is the interstandard variation is always larger than the intersubject variance. So the message is it's important to correct this thing, right? So we also did a sensitivity analysis. You can see this one is the green one is a T value. That means how much T will contribute to your total signal. And we also trying to investigate the B value and the number of B0. And you can see how this T is important in your study. So the thing I didn't show here is we are right now working a model trying to correct this T because it's quite linear. So we're trying to using a linear model to correct the value, but it's not easy. We are still working on. But if we are not interested in these details, you just want to remove this inter-center variation, as last night the Xianya Yuan they want to collaborate with us. I will just say the deep learning method will just give you excellent outcome to remove this inter-scanner variation. But it's a black box. You know nothing that does, but it'll just give you very nice results. Okay, so I think that's has been a lot for the TD impact on diffusion MRI. And for the third part, I'm going to discuss a little bit about the multi-echo functional MRI, which we are still working on. So for the diffusion MRI and the previous sequence, I'm always using the scenario of spin echo. That means you have 180 pulse to form the all the spins to refocus together to form one echo. But there's actually the other way to form an echo in MRI. It will use this linear field inhomogeneity introduced by the gradient system again. So this is a very constant field. That means you go into the scanner, your brain or your body will experience. Everywhere is ideally everywhere is 3 Tesla, right? So that's a very homogeneous field. Then in this homogeneous field, that means all the spins will rotating the same lambda frequency. But if we apply the constant field like the GZ or GX, you can determine whatever direction you want. Because we have this GX, GY, GZ by any combination of both of them. Then you can, if you apply a constant field made by this GX, that means along the X direction, the magnetic field will change just subtly. Is comparing to our B0 is a very small change. But even though this change is quite small, you can still causing the spin will process a little bit different from each other. That means from the left side is much slower and then the right side is much faster. This frequency difference will give you, because the phase equals to frequency times to time. Then this difference in frequency will give you the difference in phase. And the larger the phase distribution, the smaller the signal you will get. This is how the gradient system works. The interesting is, if you apply a bipolar pair of bipolar gradients, that means it has a negative part and the positive part. The important thing is the negative part, the area of the negative part and the positive part is the same. This is like when you have these negative parts gradients, the spins will just spread away in the whole plane. But if you change the direction of these gradients, that means like the teachers, we are calling all the spins come back, but in the same speed, right? Then, or maybe if the amplitude is the same, then it's the same speed. You can also in different speed, but the time has to be longer. But eventually, all the spins will come together if these two areas are the same. Then right here we'll get an echo because all the spins just come together. This is the time we say an echo is formed. And by this way, we actually get a gradient echo comparing to previous echo. I call it a spin echo. So you have this is a negative part and this is a positive part. You start from here. You can do this alpha. The flipping angle can be like, for the most simple way is 90 degree. You start to excitation here, then you got a gradient echo in the middle of this positive gradient, which is the T. The difference, the time duration between these two, the RF and this echo center is a T value, as I defined in spin echo. The difference comparing to the spin echo, this gradient echo will measure it's not measuring the T2 signal. It will measure the T2 star signal. The difference between this T2 star and the T2 is T2 star signal will also account for the inherent field inhomogeneity. That means when you lying in the scanner, because the tissue inhomogeneity of our body, then in different places like the air and the tissue, the interface will have different susceptibility value. Like this susceptibility will give you the field inhomogeneity. And with gradient echo, you can actually the T2 star value signal will take the inhomogeneity in the signal. Okay. So as I mentioned, this gradient echo is quite sensitive to our field inhomogeneity. One source of our field inhomogeneity is the deoxygen hemoglobin. We know the oxygen hemoglobin and the deoxygen hemoglobin, the difference is their susceptibility. When this is the source of our both signal, which we use for functional MRI, and as I mentioned, this because of this T2 star is quite sensitive to our bold change, and we use this gradient echo EPI acquisition for most functional MRI study because it's the gradient echo sequence is quite faster. The acquisition is quite faster, and with working together with this EPI method. And another thing is because the gradient echo doesn't have 180 pulse, then that means the total energy during the scanner add into your body, the RF energy will be much lower than the spin echo sequence. But in most functional MRI study with gradient echo sequence, we only use single TE value. That means this T value will set up around 30 milliseconds for the best bold contrast. This is a very simple gradient echo EPI bold image I collected from our Prisma scanner. You can, because it's a very good field homogeneity, you can get quite a nice GI EPI image like this. The topic today I'm going to say is I trying to introduce this multi-echo method. This is I'm saying it's quite advanced compared to the signal TE acquisition. That needs the high performance gradient and also needs the simultaneous multi-slice technique. That means you can still collect the whole brain, but you use a much shorter TE, or maybe even multiple TEs. With multiple TE, it actually means you do the previous D phase and loop phase again and again, as possible, several times within the single TR. For example, if you can do a 3 or 4 echoes within each TR, which the TE time for each echo will range from around 10 millisecond to 60 milliseconds. But you don't want to make your TR value to be too longer. So when you have these multiple TE values, as I'm showing here, you have previously you have only this 30-second echo, but now you have 3 echo or more echoes. Because all the echoes the signal is actually we're assuming it's following this equation. It's a T2 star decay. Then you can, with this thing, you can actually fitting the signal to get this as long as and also the T2 star, as I'm showing here. This is as non map and the T2 star map. It's not this T2 star map is a semi-quantitative value. It's not just a signal contrast. Another good thing is, as proposed by Kundu in 2012, you have this short TE. That means the image distortion will be much better than the longer TE. With longer TE, like the TE value set to 15, this frontal lobe region, you have a very big or very severe signal loss here, because the susceptibility artifact I mentioned a little bit earlier. Then you can do a weighting calculating in this very simple way. You can combine all the echoes together. You will get a combined image in this one. Then you will fill up this hole, which you cannot see any reliable signal with the single TE imaging method. This is a way one benefit with this our multi-echo technique. Another important technique is we know the functional MRI signal is affected by a lot of noise, like the head motion, respiratory, the cardiac signal, and thermal noise. And we're assuming the only signal we are interested in is, because we are interested in this bold signal, which is T2 star sensitive. So if some signal is not T2 star, it's not following this T2 star decay, we say is some signal we are not interested. So it's quite straightforward. When you have this TE, multiple TE acquisition, and you run different TR, for example, you have 500 frames, then you can do a ICA denoise. This ICA denoise or multi-echo is not straightforward, so I just gave a brief example here. So if the signal is not a linear to, if you do a change like this, you determine this value. It's not a change along the TE. That means the signal is something you are not interested in. It's not a T2 star sensitive. And then this one, for example, this one, but you want to keep all the signal like this. Here I'm showing an example saying this is the up row is showing the head motion information. You can see a big head motion here. This head motion is some artifacts, a very, very important artifact in functional MRI, but we know it's not T2 star related. Then you can see in the this is combined. If you only combine the multi-echo signals, you cannot remove this head motion. And this is a signal. I think this is a S9 dependent, which is the non-bold like. That means it's not the T2 star sensitive signal. But if we can extract the T2 star signal, you can see this motion artifact is just removed. Very straightforward. You can use this method, this multi-echo method, to improve your study. For example, we previously run a task, a facial recognition task. This is a collaboration with a psychology department professor. So this work is still in preparation, but the result is very clear. You can see this anterior temporal lobe here, the region is a part of the facial cognition network. Then you can see with this multi-echo denoise method, we can see big activation here, but with the single echo strategy, you cannot observe the activation somewhere here. And we also do calculate the SNR of this image, this activation voxel numbers. This is a peak SNR. This is a activation voxel you can get from the different strategy. The blue one is the multi-echo method. The orange one is the single method. So you can always see the benefit from this multi-echo method. The right example is from this literature by Puckett in 2018, and they are doing a motor task, and they want to see, they are interested in the basal ganglia area. So I think this is the single echo activation map. This is a multi-echo activation map. You can just visualize the difference between each other. And for quantitative comparison, this gray guy is the multi-echo. This is the white guy is the single echo. You can see the difference very easily. So this is the two example on task activation of MRI. And we can also go to the resting state. Before that, I want to introduce a little bit about the reliability analysis. There's a great concern on validity and the reliability of functional MRI. That means the validity means this is a true effect, and this is a sub effect you observed with your study. And there's a difference between these two is the accuracy of your study, and the dispersion of this signal, your observation is the precision. That means if sometimes you got your results quite repeatable between each experiment, it's quite reliable. But if the mean effect is not localized in the central part, is a true effect. That means the result is not valid. We are always expecting our results could be both reliable and valid. But I believe in functional MRI, we have no idea most of the time we have no idea about our true effects. We can only expect mostly we want to expect our experiment could be reliable. The one metric to measure this reliability is the intra-class correlation. It's defined in this way. You have this between subject variance. That means you have a group of subjects. Then you can measure this between subject variance, and you can also you measure also each subject multiple times. Then you can define the within subject variance. You want to keep this within subject variance as low as much as the best, and you want to then in that way, if this VB within subject variance is the same, keep still, then the smaller this within subject variance, this ICC value will go larger. Then we have some just qualitative threshold. If this ICC value is larger than 0.75, we say this study is quite reliable. If it's below 0.5, then we say this study could be not that reliable. You want to be pay great cautious with your experiment. As I just mentioned, if you are only interested in to reduce this within subject variance, deep learning will give you some, just like a very useful tool. This is not a function MRI study. This is a diffusion study my group did before. So I have the same subject to run twice. The first scan, the second scan, each dot is one region in the brain. So you can see these are from the same subject with the same imaging settings. You can see the difference between the two scans. This is something I'm saying is not reliable. But you do this deep learning to remove the scanner artifacts, then your result will be much better, as I'm showing here. That means we improve the within subject variance, we reduce the within subject variance, and we improve the reliability. This is quite a simple example. We come back to this our function MRI study, which we're showing here. This is from the literature by Link. It's I believe it's Cornell University. So they did a two very good study on this with this multi-echo experiment. First one is published in 2020 in the Cell Report journal. So they measured like if you have your subject run like 30 minutes in the scanner, and you just measure the functional connectivity as one important metric in function resting state function MRI. So the aim is if we can reduce the scan time from 30 minutes to like 5 minutes, 10 minutes, or even more than that, 15 minutes. So how long you can the scanner time can give you the same stable functional connectivity value you measured in 30 seconds. So I hope I explained the idea clearly. So you have this the goal like the FC value determined by the 30 minutes. Then you change the scan duration to see how close to our goal. Then with multi-echo, this is a optimized combined multi-echo study. So that means when you have this 15 minutes scan, you almost get the final stable functional connectivity as they claimed in their paper. Then I think, okay, so the last law is the single echo case. This is the T value is around 30 milliseconds. So you can see, even though you increase to 15 minutes, you can never get the result look like we got here. That means no matter the scan time you increase, you got a little chance to get a stable functional connectivity. That's why I think Liu Heseng in Beida, he claims in his individual study using functional connectivity, he claims 30 minutes is the minimum scan length for using his method. Another thing is there are some brain region because this gradient echo EPI we are using is a very severe imaging distortion in some part of the region, like this is I think it's a subgenus part of the ACC, the 西下部 ACC, the part of ACC area, anterior cerebral cortex. So with this region, because it's very close to our to the air, so you have severe susceptibility artifact when the T time is quite long. For example, you can see here with the T around 30, you can still get some signal, but to around 50 milliseconds, the signal in this region just go away. You cannot get any signal. And the other thing is I think is the lateral prefrontal cortex. It will have some artifact. The signal will be judged out. This is a image distortion. This is a signal loss. You can see these two regions, they have different T2 star value, right? One is 19, the other is 46. Then you do a comparison between multi-echo and the single echo. The message is no matter like you are doing functional connectivity analysis, which Samsung did a lot. So if you are interested in general part of the ACC, you can get this functional continuity map. I think which everyone can see the difference from this single echo. The thing is, so yellow also brighter. The map here is this means the result would be better. So we want our result always to look like this way instead of this one. So this, but the unhappy thing is even though you're using 6 hours with your single echo, that's quite very long. No one can stand for like such a long scan. The reliability map will still not as good as this multi-echo. So that means the single echo has no chance to catch the multi-echo method. Okay, so this is the literature results. So we also ran our own study. We recruited 27 healthy subjects, and we ran our own functional MRI study with our parameter setting TR value equals to 1,300. Then we have 4 echoes from 12 to around 70. Then we keep almost the same thing, but we run the same subject again with a single echo functional MRI, which is a independent scan. Then in this case, we only change the T value to 30 seconds and the acceleration with simultaneous multi-slice factor to be from 3 to 2. The other thing is the same. So we hopefully will get quite a fair comparison between these two scans. So this is our this is our results, preliminary results. We are interested in some local instead of because Lynch has already started investigating the functional continuity a lot. So we want to just to look at the local signal. This is the amplitude of the voxel, the signal, how much the power you can get. Then you can see this is the measures the amplitude of low frequency fluctuation. This is our two different data processing of multi-echo. This is a single echo. So you can see the difference between from this one to the other one. These two looks quite similar, right? But if we move to the ICC, which means I defined previously about the reliability, you can see how much the difference from this, how much the benefit this multi-echo method can bring you in your study. So you can also do this whole brain map, the surface map. You can also to look at the different regions. The message is the same. So amplitude of the signal is one metrics we use, especially in China, a lot. And the red hole means local signal similarity. Like you have 20 voxels together locally. You compare their signal correlation between each other. Then this is regional homogeneity. We also do this comparison, and I think the idea or the message is the same with previous ALF study. So mostly each of the things is the functional gradients, which Hanson also interested a lot. So we also run some with some public code to analyze our data. Then you get this graded 1, this is graded 2. You got this single echo result. You can get this multi-echo result. I cannot say which is the correct. Because as I mentioned, you cannot define your accuracy. We have no true effect as we previously defined. But you can see the reliability. This is ICC. You can see the reliability, the difference between this single echo and the multi-echo. So this is I think it's the last slide I got. So this is the whole brain map. We want to the other important thing I think is very important is to try to look at the scan duration effect. That means how long you can get a reliable result. As I defined the ICC, if your ICC value is below 0.5, that means this measure could be not as good as you expected. It's not reliable. Then This is 0.5 here. So this is the amplitude of your signal. With the single echo, this yellow one is a single echo. With this single echo study, you can never get, from this plot at least, you can never get a chance to reach the 0.5. And you can get this thing repeated from this is amplitude, this is regional homogeneity, this is a gradient analysis. So the worst case is from the functional gradient analysis. You can see with single echo, the ICC value is always, with single echo, is always below 0.3. It's far away from 0.5, our threshold want to reach, right? But with this multi-echo, when you have this 350 TR, that means around, I think it's around 6 or 7 minutes, then you can get a chance to reach 0.5. So ongoing study we are running now is trying to increase the scan length to see if with this multi-echo acquisition method, if we got a chance to reach 0.75. So and this is not the first time we observe this result. It's actually in the Lynch's 2020 paper. They also did a reliability analysis, but their reliability is different from our case. In our case, we are caring about the intersubject variance, but they are just trying to get a stable functional connectivity. But I think the final message is quite the same. In some region like this cortex, thalamus, you just get no chance, even though the scan time is quite long. It's 30 minutes already. No one can take it. So with 30 minutes single echo study, you get no chance for this region. You get no chance to get quite reliable. The color is the green region, green zone. So I think these two results give us an indication. Maybe in future study, we want to replace single echo scale acquisition with our multi-echo acquisition. And this is the project we are collaborating with Senior. We want, if we can get some good result and we can persuade the China's children project to replace current acquisition method. So with that, I want to summarize my talk very briefly. So in 3 parts, I just introduced briefly about the echo in function in MRI and the echo time. How do we define the echo time? And the second part is I briefly talked about the microstructure model and how important this T will impact to our observation. And the last part is I want to say is a multi-component signal. Even though we only collected the both signal, but we can separate the both signal into different components. This the T2 sensitive and the non-T2 sensitive. So with this multi-component signal, you can get a much more reliable result. I want to finish my talk here, and thank you for your attention.